look very much like the pictures that Mr. Lowell had drawn. And nevertheless, his ideas sponsored the fiction writers to go on with these fanciful ideas that there were humanoids living on Mars and the War of the Worlds. Some of you may remember this as children, the older people in the room. Terrified much of the radio audience in 1937, was it? I think it was about then. And it was a broadcast of Orson Welles featured as the principal radio voice. And it was broadcast without any preamble, as if it were a news announcement of an actual landing of aliens from Mars that then emerged from their spaceships and began to wage war on the Earth. Well, of course, people went into panic and they stopped their cars and they wept and so forth and so on. But this, after all, remember, this was the end of the Great Depression. And people were under a great deal of stress. And they didn't have access to the sources of information we do today. Right? So this seemed like it was legitimate, and they were all panicked about it. Well, that only lasted until the end of fantasy, which I would say happened really in 1962, when an astronomer at the University of Chicago, which by the way was Professor Telesco's alma mater, although I don't know if you were there at the time that Luke Kaplan did this work or not.
1962, I think.
Thank you. But those astronomers showed they actually applied the technique called spectroscopy, split light into its various colors and wavelengths, and they were able to measure the amount of carbon dioxide in the atmosphere of Mars. And lo and behold, they found that the surface pressure was extremely low, far too low for liquid water to exist. It would be frozen. And so on. And so this was the nail in the coffin lid that said that Mars was not an Earth-like planet. All of those claims and so on were fancy, but they were fancy. And that was the end of that first phase form. Okay, so let's get on from that. How do we know whether a planet can support life or not? Well, one of the metrics that we look for is four characteristic gases. Everybody knows we breathe oxygen, right? So if you've got oxygen breathers there, you better see oxygen in the atmosphere. Living animals, we call ourselves eukaryotes, fancy name for humans and animals and plants, all excrete CO2 when you breathe, so you better see CO2 as well. And carbon dioxide. And then you ought to have water, so you know that's present on Mars. And finally, you ought to have some gases that are produced or potentially produced by biology. And methane is one of the keys. Okay, so that's on Earth. This is a little chart that shows where the methane in Earth's atmosphere comes from. In our room, this room right here, about 2 molecules in every billion molecules of gas in this room are methane. Right? So it's not a terribly abundant gas in the atmosphere, but it's a very important one. And if you look at this little wheel, you can see that approximately 20% of the methane is produced from wetlands and marshes, like right out here in the lake where you see alligators and turtles. In fact, I just saw some big snapper down there before the lecture tonight, so it's quite interesting. Some of it comes from fermentation in the gut of humans, cows, you name it. Others comes from termites, believe it or not, about 15% from termites, which are eating biogenic material and digesting that and producing methane. Some comes from coal mines, which of course coal is an organic compound, residue of life, and so on. So roughly 95 to 97% of all methane on Earth comes from biogenic processes, burning of these or consumption. A small remaining fraction comes from other sources, including geochemistry, which is a process in which hot water and carbon dioxide that are carried underground at the subsiding zones in, say, trenches at the edges of tectonic plates is carried down into the magma layers, and there it becomes superheated and it actually combines with iron oxide to consume some of that oxygen and release the methane from the hydrogen and carbon that remains. And so we know that on Earth we have both mechanisms for producing methane. The dominant one is life. Well, in the case of Mars, by 62, as I mentioned, we knew that the planet was a pretty hostile place, but we didn't know much about it. Now keep in mind that we didn't even know that there were craters on Mars, right? They had never been seen. We didn't know that it had the highest volcano in the solar system, almost 20 miles high. Imagine that, 20 miles is the summit of the Olympus Mons on Mars. Or that it had the deepest crater in the solar system, a giant crater that's almost 5 miles deep. You're standing on the edge of the crater, and this isn't the Grand Canyon, which is less than a mile deep. It's only about half a mile. You're talking about looking down 10 times as deeply into this giant crater called the Ellis Basin. It also has the largest, longest valley system, Grand Canyon of the Colorado River. Now you have seen this, you've been there, your children have seen it, they've gone for a hike down right into the trail. This is an impressive thing, but the Grand Canyon on Mars is almost 10 times longer and much deeper. So this is a planet of extremes. Okay, so Mariner 7, 4, 7, and 9, these are a series of spacecrafts. When the U.S. was learning how to send deep spacecraft to planets, sent a series of Mariners, as they were called, relatively simple spacecraft by today's standards, past Mars, and they showed that Mars was a heavily cratered body, and that it had this very thin CO2 atmosphere, a little bit of water in the atmosphere, and no vegetation whatsoever. So this was the last final thing that laid to rest this issue of this heavily forested and vegetated twin of the Earth. The next thing was in 1976, our nation sent 2 sophisticated biological laboratories to Mars. They're called Viking 1 and 2. Many of you remember that, I think. Some of the older people in the room will remember that these 2 spacecraft orbiters around the planet, and then sent these landed spacecraft to the surface, where they conducted detailed biological experiments on soil samples, which were scooped out from the dirt, put into little pyrolysis cups or little valves that contain nutrients, and the experiments looked for the CO2 that was produced from the nutrients when they were consumed by hypothetical bacteria or archaea. Well, the unfortunate thing is that, before we go on that way, let's go just to briefly mention what these were. There were actually 2 classes of life science experiments. The first one, you might say, was looking for lizards. In fact, I remember the first image that was sent back from Mars from one of these landers showed a rocky desert landscape, and some wag at the, the National Enquirer, which is a newspaper that is fond, it's actually copied all the writers are from Harvard or Yale or Princeton, but they're humorists, so they make all these fanciful images and they publish those as if they were true. So somebody got the idea, let's take some photographs of iguana lizards, and we'll just paste those on this image of the Mars surface as if there were thousands of lizards all over this Mars surface near the spacecraft. So they did that, and it was quite humorous. We all liked that. But in reality, the color camera didn't show that there was no such life on Mars. Well, the real issue was microbial life. And so there were these 3 different experiments, one to look for organics in the soil, one for actual exchange of gases between elements of the nutrient rock and the organics in the soil, perhaps microbial in nature. And finally, this one that would look for radioactive carbon dioxide that was released when microbes would eat the radioactive nutrients that were doped in the experiment. They all were negative, essentially. Well, one of the PIs thinks that he discovered life on Mars, but this has not been accepted by the community. Well, here's the image which was returned. You can see that Mars is a very sterile, dry place, and clearly no trees, no grass, no